Somewhere in the outer solar system, it is raining. Not the sudden downpour of a summer storm, and not anything a person could stand beneath and survive. But rain nonetheless, drops forming in high clouds, falling slowly through thick air, gathering into channels, carving valleys, and finally emptying into seas that stretch for hundreds of kilometers under an orange sky. This is happening right now as you listen. It has been happening for a very long time. For most of human history, we assumed this was ours alone. Rain, rivers, shorelines, the patient work of liquid wearing down stone, these seemed like the private signature of one world. We looked outward and found other places, and they were extraordinary in their own ways. Craters, canyons, volcanoes, ice, but they were still. Nothing flowed on them. Whatever rivers they may once have had were long gone, leaving only dry beds and the memory of water in the rock. Earth was the exception. Earth was where things moved. Then we sent a spacecraft to Saturn, and it carried a small probe, and that probe fell through a wall of orange haze that had hidden a world from us for 350 years. And when the first images came back, grainy, dim, taken through an atmosphere thicker than our own, what appeared on the screens in that control room was a landscape of branching channels, networks of them. Tributaries joining larger channels running downhill toward a darker plane, exactly as a river system does on Earth. The people looking at those images were seeing something no human had ever seen before, a drainage basin on another world, shaped by a liquid that was still there. The liquid was not water. At that distance from the sun, water is not a liquid and never will be. It is frozen so hard it serves as bedrock, as unyielding as granite. What flows on Titan is methane and ethane, substances we know as gases, as the fuel in a stove, as something invisible. Out there in a place where the temperature holds steady near 180 degrees below 0 Celsius, methane behaves the way water behaves here. It pools, it evaporates, it forms clouds, it falls. And so the same physics that shaped the Grand Canyon and the Nile and every coastline on this planet has been running patiently on a moon of Saturn, using entirely different materials, at temperatures that would freeze the air in your lungs solid, under a sky the color of dark honey. That is the strangeness worth sitting with, not that Titan is unlike Earth. Almost everywhere is unlike Earth. What makes Titan remarkable is how much of Earth's machinery it reproduces, and how little of Earth's substance it uses to do it. There is a thick atmosphere, the only one on any moon in the solar system, and denser at the surface than our own. There is weather with seasons that last for years. There are clouds that gather and disperse. There is rainfall and there are storms. There are lakes with defined shorelines and seas deep enough that a spacecraft could not see their floors. There are river valleys, deltas where channels widen and drop their sediment, and vast fields of dunes shaped by prevailing winds, dunes that stretch for thousands of kilometers, arranged in long parallel ridges, made not of sand but of dark organic grains. And beneath all of it, buried under a shell of ice 100 kilometers thick, there is very probably an ocean of liquid water, an enormous one, possibly larger by volume than every ocean on Earth combined. Two liquids then on one small world, one on the surface, made of hydrocarbons, cold enough to kill instantly. One deep below, made of water, kept warm by heat leaking outward from the interior, separated by a crust of frozen water that behaves like stone. Nowhere else do we know of anything like this. It is worth pausing on the scale because Titan is easy to underestimate. We call it a moon, and the word suggests something small, a companion, a satellite, a minor object in someone else's story. Titan is larger than the planet Mercury. It is the second largest moon in the solar system, and if it were orbiting the sun directly rather than Saturn, nobody would hesitate to call it a world. It is a world by every measure that matters. It has geology, it has an atmosphere and a climate, it has a surface being actively reshaped by processes that are still operating. It has chemistry of a complexity found almost nowhere else, an atmosphere continuously manufacturing organic molecules, which drift downward and settle across the landscape in dark layers. That last detail is the one that has drawn the most attention and the most careful language. Titan is not a place we expect to find life as we understand it. It is far too cold for the biochemistry that operates here, and there is essentially no liquid water at the surface for that chemistry to work in. But it is, without much competition, the best natural laboratory in the solar system for studying what happens when carbon-based chemistry is left alone for 4.5 billion years with energy, atmosphere, and liquid. Whatever processes preceded life on Earth, the assembling of simple molecules into complex ones, before anything was alive to assemble them, those processes may be running on Titan right now. Frozen partway, preserved in the cold, a record of the chemistry that came before biology, still available to be read. And so we are going back. There is a mission in development that will not roll across Titan's surface or orbit above it, but fly, an 8-rotor craft, nuclear-powered, that will lift off from one landing site, cross tens of kilometers of alien terrain, and set down somewhere new again and again over years. It can do this because Titan's air is thick and its gravity is weak, a combination that makes flight easier there than anywhere else we have ever attempted it. But all of that lies ahead. Before any of it, before the rivers and the seas, before the haze and the hidden ocean, before we consider what might be assembling itself in the cold. It is worth understanding what Titan actually is, and where it sits, and how a world this remarkable managed to stay hidden from us for 3.5 centuries after we first saw its light. Because we have known Titan was there since 1655, we simply had no idea what we were looking at. The man who found it was 26 years old, and he was not really looking for a moon. He was testing a lens he had ground himself. Christian Huygens was born in The Hague in 1629 into a family that moved easily among the intellectual figures of the age. His father was a diplomat and poet who corresponded with Descartes. The household expected brilliance, and it got it. Huygens would go on to invent the pendulum clock, work out the mathematics of centrifugal force, and propose that light travels as a wave, an idea that would take 2 centuries to be fully accepted. But in the early 1650s, he and his brother became preoccupied with a more practical problem. The telescopes of the time were poor. Their lenses suffered from severe distortion, spreading every point of light into a colored blur, and the standard workaround was to build instruments of absurd length, tubes many meters long, awkward, and nearly unusable. The Huygens brothers set about grinding better glass themselves, developing techniques that produced noticeably sharper images than anything then available. On the night of March 25, 1655, Huygens turned one of these new instruments towards Saturn. Beside the planet sat a small point of light. He watched it over the following nights. It moved with Saturn rather than against the background stars, and it circled the planet in a regular period of about 16 days. That was enough. It was a moon, only the second ever discovered orbiting another planet, coming 45 years after Galileo had found 4 around Jupiter. Huygens simply called it Saturn's moon because at the time there was no need for anything more specific. The name we use came much later, proposed in 1847 by John Herschel, who suggested naming Saturn's family after the Titans of Greek mythology, the generation of gods that preceded the Olympians, and to whom Saturn himself belonged. The same telescope solved a second puzzle in the same period. Saturn's strange changing appearance, the mysterious handles or ears that Galileo had glimpsed and could not explain, which appeared and vanished over the years, resolved under Huygens's better optics into a flat ring encircling the planet and never touching it. He announced both discoveries in a small book published in 1659. And then for 3 centuries, essentially nothing happened. This is the part of Titan's history that is easy to skip past, but it deserves attention because it explains why the eventual discoveries landed with such force. From 1655 until the second half of the 20th century, Titan remained a point of light. Telescopes improved enormously across that span, mirrors grew from centimeters to meters, photography replaced the human eye, spectroscopy opened up chemistry at a distance. Every other large body in the solar system yielded something. Mars showed polar caps and seasonal changes. Jupiter showed bands and a great red storm. even Saturn's rings resolved into structure. Titan showed nothing, a featureless dot. An orange dot, once color could be measured accurately, but a dot. Astronomers could work out its size approximately and its orbit precisely. They could see it was large. What they could not do, through any instrument, for 350 years was see a single feature on its surface. No markings, no poles, no rotation detectable by watching features come and go, because there were no features to watch. The first real clue arrived in 1944 from a Dutch-American astronomer named Gerard Kuiper, working at the McDonald Observatory in Texas. Kuiper examined Titan's spectrum, the pattern of wavelengths in the sunlight reflecting off it, and found absorption bands characteristic of methane. Something was absorbing specific colors of light before they came back to Earth, and that something was a gas. Titan had an atmosphere. It was the first moon ever shown to have one, and for a long time it remained the only one. Kuiper estimated the atmosphere was thin, perhaps a tenth of Earth's pressure or less, and composed largely of methane. He was right that it was there, and wrong about nearly everything else, but that would take another 3 decades to establish. What was clear immediately was that the atmosphere explained the featurelessness. Astronomers were not looking at a surface at all. They were looking at the top of an opaque layer of gas and suspended particles, and whatever lay beneath it was screened from view completely. The scale of what was hidden became clearer as measurements improved. Titan's diameter is about 5,150 kilometers. That figure requires context to appreciate. It is larger than Mercury, which is an actual planet by anyone's definition. It is roughly half again the diameter of Earth's moon and about 40% of Earth's. Among the solar system's moons, only Jupiter's Ganymede is bigger, and only slightly. Its mass tells a different story. Despite the size, Titan has only about a 40th of Earth's mass, and its surface gravity is roughly 1/7 of ours, very close to the moon's, despite Titan being much larger. The reason is composition. Titan is not a rocky body with a thin skin of ice. It is roughly half water ice and half rocky material by mass, which makes it far less dense than any of the inner planets. It is a world built substantially out of frozen water, with rock concentrated toward the center. Its position around Saturn matters as much as its size. Titan orbits at about 1,200,000 kilometers from the planet, over 3 times the Earth-Moon distance, and takes just under 16 days to complete a circuit. Like most large moons, it is tidally locked, keeping the same hemisphere permanently facing Saturn. A day on Titan and a month on Titan are the same thing, and each lasts just under 16 Earth days. Saturn itself sits roughly 9.5 times farther from the Sun than Earth. Sunlight arriving there is about 1% as intense as what falls on our world. That single number governs almost everything about Titan, its temperature, its chemistry, the physical state of every substance on it. Noon on Titan is dim. The thick haze absorbs and scatters what little light arrives, leaving the surface at something like the brightness of deep twilight in a permanent orange-brown gloom. The surface temperature holds remarkably steady at about 94 Kelvin, roughly 179 degrees below 0 Celsius. It barely varies between the equator and the poles, and barely varies between day and night because the dense atmosphere distributes heat efficiently and stores it. And Titan orbits Saturn, which orbits the Sun once every 29.5 Earth years. A season on Titan lasts more than 7 of our years, which means that the weather patterns we have observed there, the clouds, the storms, the shifting distribution of liquid, unfold on a timescale where a single spring lasts longer than most spacecraft missions. By the middle of the 20th century, then, we knew Titan was enormous, cold, and wrapped in an atmosphere containing methane. Everything else was inference. The only way to learn more was to go, and when we finally did, the first spacecraft to arrive discovered that the atmosphere was not thin at all, and that it was hiding the world beneath it far more effectively than anyone had imagined. In November of 1980, a spacecraft flew past Titan at a distance of about 4,000 kilometers, closer than any human machine had ever come to it, carrying the best cameras ever sent into the outer solar system. The images it returned were of a smooth orange sphere. No features, no markings, no shading beyond a faint difference between the northern and southern hemispheres, and a thin bright band of haze floating above the North Pole. Voyager 1 had been deliberately routed past Titan at the cost of the rest of its planetary tour. The trajectory that brought it close to the moon also flung it up and out of the plane of the solar system, ending any possibility of visiting Uranus or Neptune. That sacrifice was considered worthwhile because Titan was judged the most scientifically interesting object in the Saturn system. And the cameras saw nothing at all. There's a photograph widely reproduced afterward that captures the disappointment perfectly. A featureless tangerine ball, uniform to the eye, giving up not one detail of whatever lay below. But the flyby was not a failure. The cameras were only one instrument among many, and what the others found rewrote everything. The atmosphere was not thin, it was dense, denser than Earth's. Surface pressure on Titan is about 1.5 times what you feel at sea level here, comparable to the pressure roughly 5 meters underwater in a swimming pool. A person standing there, insulated against the cold and supplied with oxygen, would not feel crushed. They would feel a slight heaviness in the air and nothing worse. And the atmosphere was not primarily methane. It is about 95 to 98% nitrogen, with methane making up most of the remainder and traces of hydrogen and other compounds beyond that. That composition is remarkable for a specific reason. Earth's atmosphere is also predominantly nitrogen, around 78%. In the entire solar system, only 2 bodies have thick nitrogen-dominated atmospheres, and they are Earth and Titan, nowhere else. Venus and Mars are carbon dioxide worlds. The giant planets are hydrogen and helium. 2 nitrogen atmospheres exist, and one of them wraps a moon of Saturn. The atmosphere is also extraordinarily extended. Because Titan's gravity is weak, the gas is not held down tightly, and the atmosphere reaches far higher above the surface than ours does, detectable to well over 1,000 kilometers up, roughly 10 times the vertical extent of Earth's. In proportional terms, Titan is wrapped in a far deeper envelope than we are. So the question becomes, why is it orange? The answer is one of the more elegant pieces of chemistry in the solar system, and it begins with something breaking. Sunlight arriving at Titan is faint, but it still carries ultraviolet radiation, and the upper atmosphere is also bombarded by high-energy particles from Saturn's magnetosphere, which envelops Titan for most of its orbit. These energies are more than sufficient to shatter the molecules they encounter. A methane molecule is a single carbon atom bonded to 4 hydrogens. Strike it with enough energy and the bonds break, leaving fragments, carbon with 3 hydrogens attached, or 2, or 1. Nitrogen molecules, which are 2 nitrogen atoms bound together with one of the strongest bonds in chemistry, are harder to break but not immune. The most energetic radiation splits them as well. What follows is the interesting part. These fragments are unstable and highly reactive. They do not remain fragments. They collide with each other and with intact molecules, and they combine, building larger structures than the ones they came from. 2 carbon atoms join, then 3. Nitrogen atoms are incorporated into carbon chains. Rings form, rings link into sheets. The process runs continuously, high in the atmosphere, and it builds upward in complexity. From methane to ethane and acetylene, from those to more elaborate hydrocarbons, from those to large molecules containing dozens or hundreds of atoms including nitrogen, and eventually to solid particles. Those particles are called tholins, a term coined by Carl Sagan and Bishan Carr in the late 1970s, from a Greek word meaning muddy, to describe the brownish substances they produced in laboratory experiments simulating exactly this chemistry. Tholins are not a single compound. They are a family of complex organic solids, poorly characterized even now, varying in composition depending on the conditions that formed them. And they are orange, deep reddish-brown in bulk. They absorb blue and green light strongly and reflect the red end of the spectrum, which is why Titan appears the color it does. These particles form high up, perhaps 500 kilometers or more above the surface, and then begin to fall. They are extremely small, so they descend slowly, drifting downward over months or years, clumping together as they go. The result is a haze that is not a thin layer but a permanent, deep, globe-spanning smog, extending through much of the atmosphere's height. It is this haze, rather than the gas itself, that made Titan opaque. Voyager's cameras were photographing suspended particles hundreds of kilometers above the ground. The haze has structure too. Voyager detected distinct layers within it, and later observations resolved a detached haze layer floating high above the main body, a thin separate shell, hundreds of kilometers up, whose formation is tied to circulation patterns in the upper atmosphere. Something else the haze does is regulate temperature, and it does so in two opposing directions at once. The atmosphere produces a greenhouse effect. Methane, hydrogen, and nitrogen together trap outgoing infrared radiation, warming the surface by roughly 20 degrees above what it would otherwise be. Without it, Titan would be considerably colder than it is. But the haze also produces the reverse, sometimes called an anti-greenhouse effect. The particles absorb incoming sunlight high in the atmosphere before it can reach the ground and radiate that energy back to space. This cools the surface, and the cooling is larger than the warming. The net result of having an atmosphere at all is that Titan's surface is colder than a bare airless rock at the same distance would be. The two effects together produce the striking stability of Titan's climate, a surface temperature that varies by only a few degrees anywhere on the globe, at any time of day, in any season. And the tholins do not stay airborne. Having formed high above and drifted down, they eventually reach the ground and accumulate. Everything on Titan's surface is dusted, coated, or in places buried in this material, an organic sediment raining continuously out of the sky, deposited over billions of years. Estimates of the accumulated depth vary considerably, but the quantity is large enough that some of Titan's most prominent landforms appear to be built out of it entirely. Which means the veil is not simply an obstruction. It is a factory, running without pause, converting the simplest carbon compound there is into the raw material of complex organic chemistry, and then delivering that material to the surface. But there was still a question the Voyager data could not answer, and it was the one that mattered most. Methane in an atmosphere does not last. Broken apart by radiation and converted into heavier compounds that fall out as solids, the entire methane supply in Titan's air should be exhausted in a matter of tens of millions of years, an eye blink compared to the age of the solar system. The methane is still there, which means something has to be replenishing it. There's a number worth holding onto. On Earth, water can exist as ice, as liquid, and as vapor, and all three occur naturally within the ordinary range of temperatures our planet experiences. That is not a small coincidence. It is the reason this world has weather. Methane freezes at about 91 Kelvin and boils at about 112. Titan's surface sits at 94. Which places methane on that moon in precisely the same position water occupies here, near enough to both of its transition points that it can shift between states as conditions vary, and therefore capable of doing everything water does: evaporate, condense, fall, pool, flow. It is one of the more remarkable accidents in the solar system. Titan is not the only cold place, and methane is not rare. But the specific coincidence of a world whose surface temperature happens to land in the narrow window where methane behaves like water, and which also has enough gravity to hold an atmosphere, and enough of the substance present to fill lakes, appears to have happened exactly once within our reach. So Titan has a hydrological cycle without hydrology, the same architecture, running on entirely different chemistry. Begin at the surface. Liquid methane mixed with ethane and dissolved nitrogen sits exposed to the atmosphere in lakes and seas and in damp ground. It evaporates slowly because the air is cold and already carries a substantial burden of methane vapor, but continuously. The rate is highest where sunlight is strongest, which on Titan means wherever the season has placed the sun overhead. The vapor rises, and here the differences from Earth begin to assert themselves. Titan's atmosphere is dense and its gravity is weak, a combination that makes the air sluggish. Convection is slower and gentler than in Earth's atmosphere. Air rises reluctantly, over larger distances and longer times. But when convection does take hold, the depth available is enormous. Titan's troposphere, the layer where weather happens, extends some 40 kilometers upward, roughly 4 times the depth of ours. Within that column, methane vapor cools as it rises, reaches saturation, and condenses into droplets. Clouds form. They are not common. For much of the time, most of Titan's sky is clear of anything but haze, and this puzzled observers for years. An atmosphere that ought to produce clouds constantly appeared, most of the time not to. What emerged from long-term observation is that Titan's weather is intermittent and concentrated. Clouds appear in specific regions, in specific seasons, sometimes as isolated bright patches, and occasionally as enormous systems covering vast areas, and then they disperse and the sky returns to empty for months. The clouds themselves sit mostly in the lower atmosphere, and they are made of methane droplets, sometimes with ethane. Ground-based telescopes in the Cassini spacecraft tracked them for years, watching them form, drift with the prevailing winds, and vanish. Then it rains. And rain on Titan is unlike rain anywhere else. The physics of a falling drop depends on gravity pulling it down and air resistance holding it back, and Titan inverts both terms: weak gravity, thick air. The consequence is that raindrops there are large, perhaps a centimeter across, roughly twice the size of a big terrestrial drop, and they fall slowly. Estimates put their descent at a few meters per second, comparable to a large snowflake here rather than a raindrop. So a rainstorm on Titan would be an oddly gentle thing to stand in, enormous drops drifting downward through dim orange light, taking their time, striking the ground softly. There is another peculiarity. Because the atmosphere is not saturated at all altitudes, a substantial fraction of what falls never arrives. Drops evaporate on the way down, producing streaks of falling liquid that fade before reaching the surface, a phenomenon we call virga, familiar from desert regions on Earth. On Titan, it may be the more common outcome, with genuine surface-reaching rainfall occurring only during the strongest storms. But it does reach the ground, and when it does, it reaches with force. The evidence is written across the landscape. Cassini's radar, which could see through the haze in a way cameras could not, mapped extensive networks of channels, branching, dendritic patterns that any geologist would recognize instantly as drainage systems carved by flowing liquid. Some are short and steep, cut into highland terrain. Others run for hundreds of kilometers across gentler ground. Some terminate in dark plains, some feed directly into seas. At the site where a probe landed in the equatorial region, the images showed rounded cobbles of water ice sitting on a damp-looking plain, rounded in the specific way that only tumbling in a current produces, worn smooth by transport in flowing liquid. Those stones had been in a riverbed. That location notably is dry now, which tells us that Titan's equatorial regions experience rainfall rarely, perhaps once in decades or centuries, but that when it comes hard enough to move stones. A desert with occasional catastrophic floods. The rate of rainfall overall is low. Averaged globally and over time, Titan receives something on the order of a few centimeters of methane per Earth year, which is comparable to a dry desert here. But it is distributed extremely unevenly, concentrated in the polar regions and in short, violent episodes. The liquid flows downhill, gathers and collects in the lowest places, and the cycle closes. Except that it does not close completely, and this is the problem the Voyager data raised. Every methane molecule that rises into the upper atmosphere is exposed to radiation, and a fraction of them are destroyed, broken apart, their carbon incorporated into heavier compounds that eventually fall out as solid particles and never return to the atmosphere as methane. Hydrogen released in the process is light enough to escape Titan's gravity entirely and is lost to space. This is a one-way leak. The methane cycle is not a closed loop like Earth's water cycle. It drains steadily. The rate of loss is high enough that the entire atmospheric methane inventory should be consumed within roughly 10 to 100 million years. The solar system is 4.5 billion years old. Titan's atmosphere should have run dry many times over. Several explanations have been proposed. The most straightforward is that methane is being resupplied from inside Titan, released from a reservoir in the interior through cryovolcanism, or outgassed slowly through the ice shell, or liberated from clathrates, cage-like ice structures capable of trapping enormous quantities of gas and releasing it under the right conditions. Another possibility is that we are simply observing at an unusual moment, that Titan's atmosphere is episodic, with methane released in large pulses separated by long dry intervals, and we happen to have arrived during a wet period. Under that scenario, Titan has spent much of its history as a very different and much quieter world. Nobody knows which is correct. It remains one of the central open questions about the Moon, and it is closely tied to what lies beneath the surface. What is not in question is the result. Right now, Titan has weather and it has standing liquid, and at the poles, that liquid has collected into bodies large enough that the only appropriate word for them is seas. For a long time, the seas were only a hypothesis, and for a while, an embarrassing one. In the years after Voyager, the reasoning seemed sound. An atmosphere saturated with methane at a temperature where methane condenses over billions of years of accumulation. Where does it all go? The obvious answer was that it pools. Some researchers proposed that Titan might be covered by a global ocean of liquid hydrocarbons, kilometers deep, with no land at all, a smooth world entirely submerged. Then radar observations from Earth in the 1990s came back showing a surface that reflected like solid ground, not like a global sea. The ocean hypothesis collapsed. For a decade afterward, the question of whether Titan had any standing liquid at all was genuinely open, and the mood tilted toward no. The answer arrived in July of 2006 from a spacecraft that had been in orbit around Saturn for 2 years. Cassini carried a radar instrument capable of penetrating the haze completely, mapping the surface in strips as the spacecraft passed overhead. On a flyby over the northern high latitudes, the radar returned something unmistakable, patches of terrain that were almost perfectly dark, radar black. Surfaces so smooth that they returned essentially no signal at all, scattering the radar beam away rather than back. There is only one common way for a natural surface to be that smooth over that large an area. It has to be liquid. And the shapes were right. The dark patches had shorelines, irregular and bayed, with what appeared to be flooded valleys and islands and channels feeding into them. They looked, in outline, like lakes on Earth photographed from orbit. Over the following years, as Cassini's radar built up coverage of the polar regions, the extent of it became clear. Titan has hundreds of lakes and several seas, and they are almost entirely concentrated near the poles, the great majority in the north. The largest is Mare. It is enormous. Its surface area is roughly 400,000 square kilometers, which makes it larger than the Caspian Sea, the biggest enclosed body of water on Earth. It is not a simple basin, but a sprawling, complex structure with multiple large lobes connected by narrow straits, extending across a substantial fraction of Titan's northern polar region. One of those straits, informally nicknamed after the Strait of Gibraltar, is a narrow channel where liquid must move between two major basins, and where tidal currents driven by Saturn's gravity are expected to run strongly. Its depth was measured by a technique that is remarkable in itself. Cassini's radar could, in some passes, detect two returns, one from the liquid surface and a second, weaker one from the seabed below. The delay between them gives the depth directly. This works only because liquid methane and ethane are extraordinarily transparent to radio waves, far more so than water, which absorbs them heavily. Titan's seas are, to radar, almost as clear as air. In parts of Mare, no bottom return came back at all. Either the sea there is deeper than the instrument could sound, or the composition absorbs more strongly than expected. Measurements in the main basin suggest depths of at least 100 meters and quite possibly over 300. Ligeia Mare is the second largest, covering roughly 130,000 square kilometers, comparable to Lake Superior and Lake Huron combined. Here the radar did reach bottom, and the result was a clean depth measurement of about 170 meters at its deepest point. Ligeia is notably smooth-shored and relatively simple in outline, and it is fed by a striking network of river channels visible entering it from the surrounding terrain. Punga Mare is the smallest of the three named seas at around 6,000 square kilometers, but it holds a particular distinction. It is the body where Cassini detected what appeared to be waves, not large ones. The measurements suggested ripples of a few centimeters, moving at perhaps a meter per second, which is barely anything, but which had been surprisingly hard to find. For years the seas appeared glassy and utterly still, and the absence of waves was itself a puzzle until seasonal wind patterns were better understood. Beyond the three seas lie hundreds of smaller lakes, and these have their own character. Many are small, tens of kilometers across, with steep, sharply defined edges and remarkably round outlines. A number sit on raised terrain rather than in low basins, perched on plateaus with ramparts around them. That geometry points to a specific formation mechanism, and the leading explanation borrows from Earth. On our planet, in limestone regions, groundwater dissolves the bedrock from below, and the surface collapses into sinkholes, producing what geologists call karst landscapes. Titan may have something analogous, liquid methane dissolving soluble material in the crust, likely organic solids accumulated from the haze, and the ground subsiding into the resulting voids. Steep-sided, rounded depressions are exactly what that process produces. There are also empty lakes, basins with the right shape, the right shorelines, the right feeding channels, and no liquid in them. Dry beds, some show bright rings around their margins, consistent with evaporite deposits, the residue left behind when a liquid evaporates and drops whatever it was carrying in solution. On Earth, the white crusts around dried salt lakes are the same phenomenon. On Titan, the residue is organic rather than mineral, but the process is identical. The composition of what fills them is a mixture rather than a single substance. The seas are dominated by methane and ethane in varying proportions, with dissolved nitrogen and traces of propane and other hydrocarbons. Ligeia Mare appears to be strongly methane-rich. Others seem to carry more ethane. The difference matters because methane evaporates more readily than ethane, so a body that has been sitting for a long time without replenishment should become ethane-enriched over time, the way a puddle of mixed liquids concentrates the less volatile component. The physical properties would make the experience of standing beside one deeply strange. Liquid methane is less than half as dense as water, and its viscosity is lower. It is thinner, more mobile, quicker to run. Anything you dropped in would sink faster than it would here. And because Titan's gravity is 1/7 of Earth's while the air is dense, waves behave differently too. They should be taller and travel more slowly, rising in long, lazy swells. Perhaps the most striking asymmetry is geographic. The overwhelming majority of Titan's standing liquid is in the northern hemisphere. The south has a handful of lakes and one modest sea, and vastly more dry basins than filled ones. The likely explanation lies in the orbit. Saturn's path around the Sun is slightly elliptical, and the timing works out such that southern summer on Titan is shorter and more intense, while northern summer is longer and milder. Over long periods, that imbalance should drive net transport of volatiles from one hemisphere to the other, evaporating liquid from the south and depositing it in the north. If that is right, then the distribution is not permanent. Over tens of thousands of years, as the orbital geometry slowly shifts, the seas should migrate. The north will dry and the south will fill, and then it will reverse again. Titan's seas move. They simply move on a time scale that makes our own ice ages look brisk. Cross Titan's equator in any direction, and you will travel through sand, thousands of kilometers of it. arranged in long parallel ridges that run east to west with extraordinary regularity, stretching sometimes for more than 1,000 kilometers without interruption. They cover something like a fifth of Titan's entire surface. By area, this is the largest known dune field in the solar system. When Cassini's radar first revealed them, the interpretation took a moment to settle. The features looked exactly like the linear dunes of the Namib Desert or the Sahara, the same shape, the same spacing, the same tendency to divert around obstacles and reconverge downwind. But nothing about Titan's environment suggested a place where wind should be moving material efficiently. Surface winds there are gentle, typically well under a meter per second, barely enough to stir dust. The resolution lies in the properties of the material and the air. Titan's atmosphere is dense enough that a slow wind carries considerable force, the same reason a gentle current in water can move gravel that a stiff breeze in air would not budge. And the grains themselves are unusually easy to lift because they are not rock. They are organic. The dunes appear to be built from the solid particles that rain down out of the haze, tholins, accumulated over millions of years, aggregated into grains roughly the size of coffee grounds. Dark, lightweight, and abundant, Titan's dunes are made of the sky's exhaust. The dune ridges themselves are impressive structures, typically 1 to 2 kilometers wide, spaced a few kilometers apart, and rising perhaps 100 meters, comparable to the largest dunes on Earth. Between them lie flat interdune corridors where the underlying surface shows through, brighter to radar, suggesting exposed water ice. Their orientation carried a small mystery. The ridges indicate net sand transport toward the east, while models of Titan's near-surface circulation predicted westward flow at those latitudes. The likely resolution is that the dunes record not the average wind, but the rare strong brief, powerful eastward gusts that occur around the equinoxes, when Titan's atmospheric circulation reverses and storms are most vigorous. The landscape remembers the exceptions rather than the routine. Beyond the dune seas, the terrain changes character. Titan has mountains, though not many and not tall. The highest known peak rises around 3,300 meters in a ridge system near the equator informally named after the Mithrim Range. Most are far more modest, a few hundred meters, worn and rounded. Their limited height is a consequence of what they are made of. Titan's bedrock is water ice, and at 94 Kelvin, water ice is genuinely rigid, roughly as strong as rock. It can hold up a mountain, but ice deforms over long timescales more readily than rock does, and mountains on Titan face a second problem that mountains on airless worlds do not: erosion. Rain falls, rivers cut. Material is transported away and deposited elsewhere. Titan is one of the few places in the solar system where landscapes are actively worn down, and the mountains show it. They are eroded, dissected by valleys, and clearly old. How they formed is not fully settled. Some appear to be tectonic, produced by compression of the ice shell, possibly when the interior cooled and contracted. Others may be the remnants of impact structures, so heavily degraded that only fragments of the original rims remain. Which brings up something conspicuous by its absence. Titan has almost no craters. Fewer than 100 impact features have been confidently identified across the entire surface, a startlingly low number for a body that has been exposed to bombardment for 4.5 billion years. Neighboring moons in the Saturn system are saturated with craters, their surfaces recording the full history of impacts since the solar system formed. Two things are erasing them. The thick atmosphere destroys smaller incoming objects before they arrive, which explains the shortage of small craters specifically. And everything else, the rain, the rivers, the migrating dunes, the steady sedimentation of organic particles from above buries and degrades what does form. Estimates place Titan's average surface age at a few 100 million years, which by planetary standards is young. Some regions are younger still. The largest well-preserved impact structure is Meneva, about 400 kilometers across in the northern equatorial region, a multi-ring basin, visibly softened, with river channels cut into and across it. Selk crater at roughly 80 kilometers is far fresher and has become important for a different reason. It is a place where an impact would have melted water ice and left it in prolonged contact with surface organics, which is precisely the combination of ingredients that interests chemists. Then there are the plains, which cover more of Titan than anything else. Large stretches of the mid-latitudes are remarkably flat and featureless to radar, moderately dark, extending for thousands of kilometers. These are informally called the undifferentiated plains, an honest name for terrain nobody has fully explained. The favored interpretation is that they are vast accumulations of organic sediment, material transported from elsewhere by rivers and wind and deposited in low-lying areas, blanketing whatever topography lies beneath. At the other extreme sits Xanadu, a continent-sized bright region near the equator, roughly the size of Australia. It was the first surface feature ever detected on Titan, visible in infrared images from the Hubble Space Telescope in the mid-1990s as a bright patch that persisted as the moon rotated. To radar it is rough and complex, laced with river valleys, dotted with hills, and what appear to be heavily degraded craters. It is probably among the oldest terrain on Titan, high standing ground that has resisted burial. And across all of this runs the drainage. River valleys appear at nearly every latitude examined, in styles that differ meaningfully from place to place. Near the poles, the networks are branching and dendritic, the signature of distributed rainfall over a broad catchment. In the equatorial regions, channels tend to be shorter and steeper, running in straight lines that follow fractures in the crust rather than the local slope, the signature of infrequent, intense flow through pre-existing weaknesses. There's layering here worth noticing. The surface is stratified by latitude in a way that reflects the climate. Seas and lakes at the poles, dunes at the equator, plains and eroded highlands in between. It is a world with climate zones, and the geology records them. One thing the surface does not obviously show is volcanism. Several features have been proposed as cryovolcanic, places where liquid water and ammonia might have erupted from below and frozen on contact, the icy equivalent of lava. A dome-like structure named Satrapatara is the most frequently cited candidate, with what appears to be a flow extending from it. But the evidence has stayed ambiguous, and alternative explanations involving erosion and deposition remain viable. Nothing has been observed erupting. That absence matters more than it might seem, because it bears directly on the methane question. If nothing is bringing material up from inside, the atmospheric methane has no obvious source. And the reason cryovolcanism is even plausible is that Titan's interior is not a solid frozen mass. Beneath the ice that forms its mountains and riverbeds, there is very likely a great deal of liquid, and it is not made of methane. The evidence for it came not from any camera or radar, but from watching how a moon bends. Titan's orbit around Saturn is slightly elliptical, which means the tidal forces pulling on it vary over the course of each 16-day circuit, stronger when it swings closer, weaker when it moves away. Any body subjected to a varying pull will flex in response. The question is how much. A rigid object, frozen solid all the way through, barely deforms. A body with a liquid layer inside deforms far more, because the outer shell is free to slide and stretch over the fluid beneath it, rather than being anchored to a solid interior. Cassini measured Titan's gravitational field on repeated close passes, timed to catch the moon at different points in its orbit. Tracking the spacecraft's motion to extraordinary precision allowed the shape of that field to be reconstructed, and the field changed as Titan moved. The moon was flexing by something like 10 meters over each orbit. That is roughly 10 times more than a fully solid Titan could manage. There is essentially one way to produce that result. Somewhere beneath the surface, a substantial layer of liquid must be decoupling the outer shell from the interior. A second independent line of evidence arrived from a stranger direction. Instruments detected an extremely low-frequency electromagnetic signal in Titan's atmosphere, a resonance in the cavity between the ground and the ionosphere. The behavior of that signal depends on the electrical properties of what lies below the surface, and the readings fit poorly with pure ice, which is a very poor conductor. They fit well with a conducting layer beginning perhaps 50 to 100 kilometers down. Salty water conducts, ice does not. A third clue came from Titan's rotation. Careful tracking of surface features over years showed that the crust does not rotate at exactly the rate a rigidly locked body should. It slips slightly, seasonally, as winds in the dense atmosphere push against it, which is only possible if the shell is not welded to the interior. 3 different methods measuring 3 different things, converging on the same conclusion. So the picture that has emerged is of a layered world, and it is worth building up from the center. At the core, rock silicate material, making up roughly half of Titan's mass, concentrated inward. Whether that core is fully differentiated into a clean rocky sphere or remains a partially mixed rock and ice interior is still debated, and the difference matters for how much heat the interior generates and retains. Above that, and this is the strangest layer, there may be a shell of high-pressure ice. At the pressures found deep inside Titan, water ice takes on crystal structures that do not occur naturally at the surface, denser phases, packed more tightly than ordinary ice, which sink rather than float. If this layer exists, it forms a floor beneath the ocean. Then the ocean itself, liquid water, tends to perhaps 200 kilometers thick, wrapping the entire moon. And above it, an outer shell of ordinary water ice, somewhere between 50 and 150 kilometers thick, which is the bedrock of everything on the surface, the mountains, the riverbeds, the floors of the seas. The volume involved is difficult to hold in mind. Titan's subsurface ocean plausibly contains more liquid water than all of Earth's oceans combined. This small orange moon, wrapped in hydrocarbon smog, may hold more water than our entire planet. Which raises the obvious question, how does anything stay liquid at that distance from the sun? Sunlight is irrelevant here, it barely reaches the surface, let alone 100 kilometers down. The heat comes from inside from 2 sources. The first is radioactive decay in the rocky core, the same process that keeps Earth's interior molten. Over 4.5 billion years, this supplies a steady, slowly declining trickle of warmth. The second is tidal heating. The same orbital flexing that revealed the ocean also generates friction, and friction generates heat. Titan's eccentricity is maintained partly by gravitational interactions with Saturn's other moons, so the flexing does not damp away. Even together, these are marginal, probably not sufficient on their own to prevent complete freezing over that span of time, which is where a third ingredient comes in. Ammonia. If Titan's ocean contains dissolved ammonia, and the chemistry of its formation region suggests it should, then its freezing point drops dramatically. An ammonia-water mixture can remain liquid at temperatures far below zero, down toward 200 Kelvin in the right proportions. That takes a marginal heat budget and makes it comfortably sufficient. Dissolved salts would contribute further, which also fits the electrical conductivity measurement. So the ocean is probably not pure water. It is likely a cold, dense, ammonia-laced, salty solution, under enormous pressure, sealed beneath a crust of ice thicker than Earth's entire crust and mantle lithosphere combined. And this is where the ocean connects back to everything on the surface. It offers the most plausible answer to the methane problem. If Titan's interior holds a reservoir of methane trapped in clathrates within the ice or dissolved in the ocean itself, then episodic release through fractures in the shell would resupply the atmosphere. That would explain why the methane has not run out, and it would explain why the surface shows possible cryovolcanic features. The eruptions, if they occur, would carry water and ammonia upward from below, freezing on contact with the cold and venting gas into the air. It also raises a question that has become one of the most carefully worded in planetary science, whether that ocean could support life. The ingredients are not obviously absent. liquid water, which is the solvent nearly all terrestrial biochemistry depends on, energy from tidal heating and radioactive decay, and potentially chemistry if the ocean is in contact with the rocky core at its base. Then water-rock reactions could release the chemical energy that sustains ecosystems around hydrothermal vents on Earth's seafloor, entirely without sunlight. Whether that contact exists is the crux. If a layer of high-pressure ice separates the ocean from the rock, the chemical exchange may be limited. Some models suggest material can still transfer through that layer over long periods. Others suggest it seals the ocean off effectively. There's also the question of whether organic material from the surface can reach the ocean below. Titan manufactures complex organics continuously and deposits them on the ground. If impacts occasionally punch through the shell, or if fractures allow material to descend, then the ocean could receive a supply of prebiotic chemistry from above, an arrangement found nowhere else we know of. None of this is evidence of life. It is a description of a place where the preconditions are not ruled out, which is a much weaker claim and an honest one. But it means Titan is two worlds stacked one on top of the other, and both are interesting for different reasons. Below, a dark water ocean under crushing pressure, possibly in contact with rock, entirely cut off from the sky. Above, a landscape of hydrocarbon rivers and organic dunes beneath an orange haze. And that upper world, the one we can actually see, does not sit still. It has seasons, and because Saturn takes nearly 30 years to circle the sun, those seasons unfold on a scale that dwarfs a human lifetime of patience. A single season on Titan lasts 7.5 Earth years, which means that a spacecraft arriving in one season and departing in another would have to stay for well over a decade simply to watch the weather change once. Cassini stayed for 13 years. It is the only reason we know any of this. The rhythm is set entirely by Saturn. Titan's own tilt relative to its orbit around the planet is negligible, so it contributes almost nothing. What matters is that Saturn's axis is tilted about 27 degrees, remarkably close to Earth's 23, and Titan orbits in Saturn's equatorial plane, so it inherits that tilt wholesale. As the planet and its moons travel around the Sun over 29.5 years, first one hemisphere lines sunward and then the other, exactly as on Earth. 4 seasons then, each running about 7.5 years, in a year that lasts nearly 3 decades. The tilt also produces something Earth does not have to contend with. Twice per Saturnian year, when the ring plane aligns edge-on to the Sun, the rings cast almost no shadow. At other times, they throw an enormous shadow band across the planet and, to a lesser degree, affect the illumination of the inner system. For Titan orbiting well outside the main rings, the effect on sunlight is small but not entirely absent. What the seasons actually do to Titan is move the weather from one pole to the other. The atmosphere circulates in a single vast overturning cell for most of the Titanian year. Warm air rises over whichever hemisphere is in summer, flows at high altitude toward the opposite pole, descends over the winter hemisphere, and returns near the surface. On Earth, our rotation is fast enough to break this pattern into 3 separate circulation bands per hemisphere. Titan rotates once every 16 days, slowly enough that the pattern stays unified, a single pole-to-pole conveyor. Twice per year at the equinoxes, that conveyor has to reverse direction, and the reversal is not gradual. It is the most turbulent period in Titan's climate, and it is when the strongest storms occur. Cassini happened to arrive shortly after northern winter solstice and remained through the 2009 equinox and into northern summer, which meant it observed the reversal directly. The cloud behavior it tracked is one of the mission's quieter achievements. During southern summer in the early years, large convective cloud systems appeared repeatedly over the south polar region, bright, transient, sometimes covering enormous areas and dissipating within days. As the years passed and the seasons advanced, that activity faded from the south and began appearing in the north. By the time the mission ended in 2017, with northern summer underway, the North Polar region was the active one. The weather migrates. It follows the sun on a decade-scale march from one hemisphere to the other, and the seas migrate with it over far longer periods. Between those polar episodes, Titan is remarkably quiet. Cloud cover is typically a small fraction of the disk, and there were stretches of years when almost nothing appeared anywhere. This is not a stormy world. It is a world of long calm punctuated by rare, intense events. The most dramatic of those events was observed in September of 2010 near the equinox, when a large cloud system developed over the equatorial region, an area that had appeared bone dry for the entire mission to that point. In the weeks that followed, the surface beneath it visibly darkened across a vast area, and the darkening then faded slowly over months. That was rainfall. A methane storm had wet an equatorial desert, and the ground stayed damp long enough to be seen from orbit before drying out. It was the first time anyone had watched precipitation reach the surface of another world and change it. The winds themselves are strange in their vertical structure. At ground level, air movement is gentle, typically well under a meter per second, barely perceptible. But wind speed increases sharply with altitude, and high in the atmosphere it becomes something else entirely. Titan's upper atmosphere is a superrotator. It circles the moon far faster than the moon itself turns, reaching speeds in the range of 100 meters per second or more, completing a lap in a couple of days rather than 16. This is the same phenomenon found in Venus's atmosphere, and its mechanism is not fully explained in either case. Momentum must be transported upward and concentrated at altitude, but the details remain an active problem. The consequence is a thick haze layer being dragged rapidly around the moon, while the ground below barely stirs. Winter at the poles produces something distinctive as well. When a polar region enters its long darkness, the upper atmosphere above it cools sharply, and a circulation pattern develops that isolates the air over the pole from the rest of the moon. Within that isolated vortex, chemistry proceeds differently. Complex organic compounds accumulate, unable to mix away, and condense into clouds of exotic ices at high altitude. Cassini watched a vortex of this kind form over the South Pole as southern winter approached, and detected within it clouds of compounds including hydrogen cyanide, condensing at altitudes far too high for methane to be involved. A hood of organic ice forming over a pole in permanent darkness, unlike anything in Earth's atmosphere. There is also a tidal component to the weather, which is unusual. Saturn's gravity raises tides in Titan's atmosphere far stronger than any the moon raises in ours, and the elliptical orbit means these vary over the 16-day cycle. This atmospheric tide contributes measurably to wind patterns and may play a role in triggering some cloud formation. And the seas respond to tides too. In the great connected basins of the north, particularly through the narrow straits between the lobes of Croc and Mare, tidal currents are expected to run at appreciable speeds, genuine flowing water, or rather flowing methane, driven by Saturn's pull on a 16-day rhythm. What all of this adds up to is a climate that is simultaneously familiar and alien. The architecture is recognizable, seasons driven by axial tilt, a circulation cell moving heat from summer to winter hemisphere, convective storms, precipitation, evaporation, tides. Every element has a terrestrial counterpart. But the timescales are stretched by a factor of 30. The working fluid is methane rather than water. The temperatures never rise above 100 Kelvin, and the whole system is wrapped in a permanent organic smog that determines how much light gets in and how much heat gets out. Titan's weather is Earth's weather, slowed down and run cold. And the reason we know any of it in this detail is that on a January day in 2005, a small probe separated from the Cassini spacecraft fell for 3 weeks through empty space and then dropped through that orange haze to find out what was underneath. It weighed 318 kilograms, measured about 1.33 meters across, and it had one working day in its entire existence. The Huygens probe was built by the European Space Agency and carried to Saturn attached to the side of Cassini, riding along for 7 years without ever being switched fully on. It had no propulsion of its own. It could not steer, could not correct its course, could not choose where it landed. Once released, it would go wherever physics took it. And it had no second chance. Everything it was designed to do had to happen during a single descent lasting a few hours, into an atmosphere whose properties were known only approximately, onto a surface that might have been solid rock, soft sediment, or liquid sea. Nobody knew which. The engineers had to design a machine that could survive all three. Huygens separated from Cassini on Christmas Day of 2004 and coasted for 20 days, spinning slowly for stability, its systems asleep apart from a timer counting down. It entered Titan's atmosphere on January 14, 2005, moving at about 6 kilometers per second. The entry itself was violent. A heat shield took the friction of deceleration, glowing at temperatures over 1,000 degrees, and slowed the probe from hypersonic to subsonic in under 3 minutes. Then a small pilot chute pulled away the back cover, a main parachute deployed, and the shield was jettisoned. From that moment, the instruments were exposed, and the descent began in earnest. It lasted 2 hours and 27 minutes. There was a problem, and it is worth acknowledging because it very nearly cost half the data. Huygens transmitted to Cassini, which relayed everything to Earth. The probe's own transmitter was far too weak to reach home directly. It used 2 redundant channels, A and B, carrying overlapping information for safety. But a command to switch on the receiver for channel A was never sent, due to a software oversight discovered too late to fully correct. Channel A was lost entirely. Most of the science survived because the redundancy worked as designed for the bulk of the data. But some measurements existed only on the lost channel, including part of the wind tracking experiment, which had to be reconstructed afterward using radio telescopes on Earth that had been listening to the probe's faint carrier signal directly, an unplanned rescue that worked remarkably well. What Huygens sent back during those 2.5 hours amounts to the only direct measurements ever taken inside Titan's atmosphere. The composition was confirmed precisely, overwhelmingly nitrogen, with methane increasing toward the surface, and traces of argon whose isotopic ratios carried information about how the atmosphere formed. Temperature and pressure were logged continuously all the way down, producing a vertical profile that remains the reference against which every model is calibrated. The lowest layers, it turned out, were warmer and more stable than expected, with a shallow, sluggish structure near the ground. Winds were measured by tracking the probe's drift. They were strong at altitude, over 100 meters per second in the upper atmosphere, consistent with the superrotation observed from orbit, and fell away sharply lower down. Near the surface, the probe was barely moving horizontally at all. And there was one detail nobody had predicted. At an altitude of around 70 kilometers, the winds nearly vanished, a narrow layer of almost complete calm, sandwiched between fast-moving air above and below. It has never been fully explained. An instrument listened for sound and detected the low rumble of atmospheric turbulence. Another measured the electrical conductivity of the air and found evidence consistent with charged particles, hinting at something like lightning activity somewhere in Titan's atmosphere, though no strike was ever directly observed. Then, as the probe descended below about 40 kilometers, the haze thinned enough for the cameras to begin returning images of the ground. What appeared was not what most of the team had expected. The first pictures showed a bright, elevated region cut by dark, branching networks, channels running downhill, joining into larger channels in a pattern that any hydrologist would recognize instantly. Dendritic drainage. Some of the channels were short and steep, others long and meandering. They all ran in the same direction, toward a broad dark plain that met the bright highlands along a boundary that looked unmistakably like a shoreline. Nobody had ever seen a river system on another world with liquid still present in the environment. The images went around the world within days. The descent continued, the cameras returning progressively closer views, and at 11:38 Universal Time, Huygens touched down on that dark plain. It landed at about 5 meters per second, a firm but survivable impact comparable to dropping from a low wall on Earth. And the way it landed told the scientists what the ground was made of. An accelerometer recorded the deceleration profile in detail. A brief hard resistance as the probe punched through a thin crust, then a softer, gradual stop as it pushed into material beneath. The comparison that circulated afterward was landing on wet sand, or on a creme brulee, a firm surface with something yielding under it. The probe settled about 12 centimeters into the ground, and a heated instrument on its underside detected a puff of methane vapor released as the warm probe contacted the surface. The ground was damp, not saturated, not liquid, but holding methane the way desert soil holds moisture after rain. Then it sent the picture. The image from the surface of Titan shows a flat, orange-brown plain stretching to a hazy horizon, scattered with rounded pebbles and cobbles. Some are 10 or 15 centimeters across, most are smaller. They sit in shallow depressions as though settled into fine sediment, and they are rounded smoothly, evenly rounded in the specific way that only prolonged tumbling in a current produces. Those stones are water ice, and they had been in a riverbed. The plain also showed subtle darker lines suggestive of past flow, and the sediment between the cobbles appeared fine-grained and organic-rich. Huygens kept transmitting from the surface for another 72 minutes, until Cassini passed below the horizon and the relay was lost. Its batteries had enough charge to continue, and radio telescopes on Earth detected its carrier signal for some time afterward, but no more data could be received. It remains where it landed, near Titan's equator, coated by now in accumulated haze fallout. The mission's significance is difficult to overstate. It is the most distant landing humanity has ever achieved. No spacecraft has touched down anywhere farther. It is the only probe ever to land on a moon other than our own, and it converted Titan in the space of a single afternoon from an abstraction into a place with a texture, a horizon, and stones you could pick up. But the deepest result was not geological, it was chemical. Instruments aboard the probe sampled the atmosphere directly and found a far richer inventory of organic compounds than the composition of nitrogen and methane alone would suggest, and hinted at chemistry considerably more complex still, happening continuously, all around it. In 1953, a graduate student in Chicago sealed a flask containing water, methane, ammonia, and hydrogen, and ran electrical sparks through it for a week to simulate lightning in an early atmosphere. When he analyzed the brown residue that accumulated, he found amino acids, the building blocks of proteins, assembled from nothing but simple gases and energy. Titan is running that experiment continuously, across an entire world, and it has been running it for 4.5 billion years. That is the reason Titan occupies the position it does in planetary science. Not because anyone expects to find something swimming there, but because it is the only place we know of where prebiotic chemistry, the chemistry that came before biology, is happening at planetary scale, right now, where it can be measured directly rather than inferred from ancient rocks. The inventory of what that chemistry produces is substantial. Beyond the methane and nitrogen that dominate the atmosphere, instruments have identified ethane, acetylene, propane, ethylene, and a range of heavier hydrocarbons. Then the nitrogen-bearing compounds, which are the more interesting group: hydrogen cyanide, cyanocetylene, acetonitrile, and larger molecules combining carbon, nitrogen, and hydrogen in increasingly elaborate arrangements. Hydrogen cyanide deserves particular attention. On Earth it is a poison, but in prebiotic chemistry it is one of the most versatile starting materials known. Under the right conditions it polymerizes, molecules linking into chains, and those polymers can yield the nucleobases that form the information-carrying components of DNA and RNA, as well as amino acids. It is present in Titan's atmosphere in significant quantities, and it condenses into clouds over the winter pole. The instruments aboard Cassini found something even more surprising in Titan's upper atmosphere: very large negatively charged molecules, with masses running to thousands of atomic units at altitudes near 1,000 kilometers. Nobody had expected molecules of that size in such a rarefied environment. They appear to be the intermediate stage between simple gases and the solid haze particles below, chemistry caught partway through the process of building itself into something substantial. Those particles are the tholins, and laboratory work has established quite a lot about what they can do. When tholins are synthesized under Titan-like conditions in a laboratory and then exposed to liquid water, they hydrolyze, and the products include amino acids and nucleobases. Multiple independent groups have found this. The relevance to Titan is direct. The surface is coated in this material, and there is an ocean of liquid water beneath the ice. Any process that brings the two into contact, whether an impact melting through the crust or fractures allowing descent, would initiate exactly that chemistry. Impact melt pools are the most concrete version of this. A large impact into Titan's icy crust would produce a body of liquid water mixed with surface organics, and modeling suggests such a pool could remain liquid for hundreds or even thousands of years before freezing solid. That is a long time for chemistry to proceed. Selk Crater, the relatively fresh 80-kilometer structure mentioned earlier, is the best studied example of a place where this must have happened. Then there is the more speculative question, and it deserves careful handling. Could something live in the methane rather than in the water? The argument for taking the question seriously runs like this. Life as we know it uses water as a solvent, the medium in which molecules dissolve, move, and react. Water has excellent properties for this, but the reasoning that only water can work may be parochial. Liquid methane is also a solvent. It dissolves different things, non-polar compounds rather than polar ones, which means any chemistry occurring in it would have to be built on entirely different molecular architecture. But different is not the same as impossible. A proposal published in 2015 explored whether cell membranes could exist in liquid methane. Terrestrial membranes are made of lipids with water-loving heads and water-fearing tails, an arrangement that only works in water. The researchers modeled an alternative built from small nitrogen-bearing molecules known to be present on Titan, acrylonitrile among them, and found that such structures could theoretically form stable membranes at 94 Kelvin. They called them azotosomes. It was a computational result, not an observation. It demonstrated that the idea is not immediately ruled out by physics. It demonstrated nothing else. The objections are serious, and they mostly come down to temperature. Chemical reactions slow dramatically as temperature falls, and at 94 Kelvin, reaction rates are lower than at Earth's temperatures by many orders of magnitude. Any metabolism operating there would run at a pace almost impossible to imagine. A generation might take millennia. Whether meaningful biology can occur that slowly is genuinely unknown. There is one observation sometimes cited as a possible hint, and it should be described with precision. Models of Titan's atmospheric chemistry predict that hydrogen produced in the upper atmosphere should diffuse downward and accumulate near the surface. Measurements did not find the expected accumulation. One speculative explanation, floated in 2010, was that something at the surface consumes hydrogen, which had been proposed years earlier as a possible metabolism for hypothetical methane-based life. That interpretation received considerable press attention. It is not held up as anything more than one possibility among several. Uncertainties in the measurements are large. The models involved have their own uncertainties. An unknown surface catalysis could produce the same result without any biology. The scientist whose work generated the finding was explicit at the time that a chemical explanation was far more likely than a biological one. That is where the matter rests, and it is worth being clear about the shape of the claim. Nobody working on Titan is claiming evidence of life. What they are claiming is that Titan is the best available place to study the chemistry that precedes life, and a reasonable place to test whether the assumptions we have built around water are actually necessary or merely familiar. There is one more consideration that makes Titan valuable, and it is about preservation. On Earth, the record of prebiotic chemistry has been almost entirely erased. 4 billion years of plate tectonics, weathering, and crucially life itself have destroyed the evidence. Any complex organic molecule sitting around on Earth's surface is eaten within hours. The transition from chemistry to biology happened here, and then biology consumed all traces of how it happened. On Titan, nothing eats anything. The organics accumulate, and the cold preserves them. Whatever complexity has been reached over 4.5 billion years is still lying on the surface, in the dunes and the sediment in the lake beds undisturbed. Which makes Titan something like a frozen record of the stage Earth passed through before life began, the same chemistry, held in place, waiting. The problem is that Huygens sampled one location for one afternoon in 2005. To read a record spread across a world the size of Titan, you would need to visit many places, different terrains, different latitudes, different histories. Which requires a machine that can move. Here is a fact that changes everything about how you explore Titan. If you strapped wings to your arms and jumped, you could fly. Not metaphorically, a human being on Titan, wearing a pressure suit and a pair of modest wings, could genuinely generate enough lift with their own muscles to leave the ground and stay airborne. It is one of the few places in the solar system where unpowered human flight is physically possible. The reason is a combination of two numbers working in the same direction. Titan's atmosphere is about 4 times denser than Earth's at the surface, which means every square meter of wing generates far more lift for the same speed. And its gravity is about 1/7 of Earth's, which means there is far less weight to lift in the first place. Multiply those together and flight on Titan is roughly 30 times easier than flight here. Which is why the next mission to Titan will not drive, it will fly. Dragonfly is a rotorcraft, a nuclear-powered drone with 8 rotors, about the size of a small car, designed to land, work, and then take off again and travel somewhere new. It is the 4th mission in NASA's New Frontiers program, selected in 2019 over competing proposals, and it represents a genuinely new approach to planetary exploration. Every previous mission to a planetary surface has faced the same constraint. Landers stay where they land and see one place. Rovers can move, but slowly. The most capable Mars rovers have covered tens of kilometers over years of operation, picking their way around obstacles, limited by terrain that can trap or damage them. Dragonfly will cover more ground in a single flight than any Mars rover has managed in its entire mission. Individual hops are planned at up to about 8 kilometers, and over the course of the mission, it is expected to travel well over 100 kilometers in total, possibly considerably more. And it will do this in an environment where flight is not merely possible but unusually forgiving. Titan's low gravity means a hard landing is far less damaging than it would be here. The dense air makes the rotors highly effective. Surface winds are gentle, typically under a meter per second, which removes the main hazard that grounds drones on Earth. The design reflects careful thinking about failure. 8 rotors are arranged as 4 coaxial pairs, 2 stacked rotors at each corner. That configuration means the craft can lose an entire rotor, and in some scenarios more than one, and still fly. There is no way to repair anything at 1.5 billion kilometers, so redundancy has to be built in from the start. The vehicle weighs around 875 kilograms and stands roughly 3 meters long. Its rotors span about 1 meter each. Instruments are distributed through the body, with cameras mounted to look forward and downward, and sampling equipment underneath. The mission profile is unusual, and it is worth understanding because it shapes everything. Dragonfly will not fly continuously. It will spend most of its time on the ground. A Titan day is nearly 16 Earth days, and the craft will typically remain at a site through a full day-night cycle, sometimes considerably longer. During the long night, it recharges, performs measurements, and transmits data. Flights are planned for daylight, roughly once per Titan day, lasting on the order of half an hour to an hour. So the rhythm is fly for perhaps 30 minutes, then work for 2 weeks, then fly again. That pattern lets a single vehicle behave like a series of landers, sampling a genuinely diverse set of locations rather than one. It also allows a strategy nobody has used before: fly ahead, photograph a candidate site from the air, and decide whether to commit to landing there, reconnaissance and exploration by the same machine. The scientific targets are specific. The landing region is in the equatorial zone, near a large dune field named Shangri-La. The initial site sits among the linear dunes, and Dragonfly will work its way across the interdune terrain toward its principal destination, Selk Crater. Selk was chosen deliberately. It is a relatively young impact structure, roughly 80 kilometers across, and impacts of that scale into an icy crust generate liquid water melt that persists for a long time before refreezing. At Selk, that liquid water would have been in direct contact with the surface organics that blanket Titan. It is, in other words, a place where the two halves of Titan's chemistry were forced together, and where the products of that meeting should still be preserved in the frozen deposits. The mission's central question is not whether life exists there. It is narrower and more answerable: how far did the chemistry get? Dragonfly will look for the specific molecules that matter, amino acids, if they are present, and their distribution. It will look at whether certain molecular forms appear in preference to others, which is a signature chemists watch for, because life on Earth uses one-handed molecules almost exclusively, while ordinary chemistry produces both hands equally. It will measure the composition of the dune material directly, establishing what the tholins actually are after billions of years of accumulation. It will also do straightforward geology and meteorology. Weather stations will record temperature, pressure, wind, and humidity continuously across many Titan days, building the first long-term surface weather record for any body beyond Earth and Mars. Seismic sensors will listen for tidal flexing and any internal activity, which could constrain the depth of the ice shell and the ocean beneath it. The instrument suite includes a mass spectrometer for identifying molecules in samples drilled from the surface, a gamma-ray and neutron spectrometer for determining bulk composition of the ground beneath the craft, cameras for both navigation and science, and the geophysical and meteorological package. The timeline is long. Launch is currently planned for 2028, with arrival at Titan in the mid-2030s and a baseline mission of a little over 3 Earth years on the surface, which is roughly 70 Titan days. That gap between launch and results is worth sitting with. Anyone following this mission will wait more than a decade after it leaves the ground before the first images come back. The team that operates Dragonfly on the surface will include people who were not yet working in the field when it was selected. But the payoff is a kind of exploration nobody has attempted. A machine moving freely across an alien landscape, choosing where to go, landing on dunes and crater floors and whatever else it finds, sampling as it travels, building a picture of a world rather than a snapshot of a single spot. Doing that autonomously, though, presents a problem that has nothing to do with flying. When Dragonfly lifts off from a dune field on Titan, there will be nobody watching in real time and nobody capable of intervening. The nearest human being will be more than an hour away at the speed of light. Send a command to Titan and it arrives somewhere between about 70 and 90 minutes later, depending on where Saturn and Earth happen to sit in their orbits. Ask a question and the answer takes the same time coming back. A round trip runs to 2.5 or 3 hours. Now consider what that means for a flying machine. A drone flight on Titan will last perhaps 30 to 60 minutes, which is to say, the entire flight will be over before the first radio signal from its takeoff has reached Earth. By the time anyone at Mission Control learns that Dragonfly has left the ground, it will already have landed successfully or otherwise, and the outcome will have been decided more than an hour earlier. There is no piloting this, there is no monitoring it, there is no aborting a flight that has gone wrong. Every flight must be executed entirely by the vehicle itself, from takeoff to landing, with no human in the loop at any point. This is the deepest technical challenge of the mission, and it is a genuinely different problem from anything attempted before. Mars rovers have autonomy, but of a limited and forgiving kind. They drive slowly, they can stop and wait, and if navigation software becomes uncertain, it simply halts and asks for instructions. A day is lost, nothing more. An aircraft cannot stop and wait. Once airborne, it is committed. It must find its way, avoid hazards, identify a safe landing site, and set itself down, all within a single continuous sequence, all on its own judgment. The way Dragonfly handles this is by breaking each flight into phases with clear decision points. Before any flight, the craft has already photographed its surroundings from the ground and on previous flights from the air. Mission planners on Earth select a target region and upload a flight plan well in advance, the direction, the distance, the general area to head for. That planning happens over days, using imagery already returned. The flight itself then proceeds under the vehicle's control. It ascends vertically to altitude, orients itself, and flies toward the designated area using inertial navigation, supplemented by visual tracking of the ground below. Titan has no global positioning system and no magnetic field useful for navigation, so the craft must determine its own position by measuring its accelerations and by matching what its cameras see against what it saw before. The critical phase is the end. As Dragonfly approaches the target area, it descends partway and surveys the ground with its cameras and LiDAR, building a map of the terrain below. It is looking for a patch that is flat enough, free of large rocks, and not obviously hazardous. Software evaluates candidate sites against criteria set in advance, selects one, and commits. If nothing acceptable appears, the craft can move on and survey elsewhere within its fuel margin. Only after touchdown does it establish contact and report what happened. Communication itself is constrained. Dragonfly carries a high-gain antenna capable of transmitting directly to Earth, which avoids depending on an orbiting relay. There will be no spacecraft in Saturn orbit when it arrives. But direct transmission across 1.5 billion kilometers from a modest antenna on a battery-limited vehicle yields a low data rate. Estimates put the return at a few hundred megabits per Titan day. That is not much. It means images will be compressed and prioritized, that not everything gathered can be sent, and that the craft must decide onboard what is worth transmitting. It also means Earth can only speak to Dragonfly when Titan's rotation has carried the landing site into view, which, given a 16-day rotation, is a substantial fraction of the time, but far from continuous. Then there is power, and here the constraint is absolute. Solar panels are not an option. Sunlight at Saturn is about 1% of what falls on Earth, and Titan's haze absorbs and scatters most of what arrives, leaving perhaps 0.1% reaching the ground. A solar-powered vehicle, there would be a very expensive ornament. Dragonfly carries a radioisotope thermoelectric generator, the same class of device that has powered every long-duration outer solar system mission. It contains plutonium-238, which decays and produces heat continuously, and thermocouples convert a portion of that heat directly into electricity with no moving parts. The output is modest, a few hundred watts, and it declines slowly and predictably as the fuel decays. A few hundred watts is nowhere near enough to spin 8 rotors. Hovering a vehicle of that mass, even on Titan, requires kilowatts. The solution is to store energy rather than generate it on demand. The generator charges a lithium-ion battery continuously throughout the long Titan day and night, roughly 16 Earth days of steady trickle. The battery then discharges rapidly during the flight, delivering the burst of power the rotors need. Then the cycle repeats. This is why flights are infrequent. The limiting factor is not fuel or wear, but how long it takes to refill the battery, and that sets the mission's rhythm as firmly as any orbital mechanics. The generator provides a second benefit that is easy to overlook. Titan's surface is at 94 Kelvin, and electronics do not work at 94 Kelvin. Batteries lose capacity, lubricants seize, materials become brittle. The waste heat from the generator, which is most of its output, since thermoelectric conversion is inefficient, is routed through the vehicle's interior to keep instruments and electronics at workable temperatures. The dense cold atmosphere, which makes flight easy, also strips heat away efficiently. Managing that balance is a large part of the engineering. The choice of landing region reflected all of these constraints together. The equatorial dune fields are relatively flat and predictable, which matters for autonomous landing. They are on the hemisphere that faces Earth at appropriate times for communication. And the terrain is scientifically valuable while being operationally survivable. The polar seas would be more dramatic, but there is no way to land a rotorcraft on a methane sea and take off again. The mission is planned to begin at a site in the Shangri-La Dune Field and work northward towards Selk Crater in a series of hops, each one a separate small expedition with its own reconnaissance, decision, and landing. There is something worth appreciating in the whole arrangement. This is a machine that will spend the majority of its existence sitting still in the cold and dark, slowly gathering energy, and then spend under an hour every couple of weeks doing the thing it was built for alone, unwatched, making its own decisions, on a world where the nearest human intervention is 3 hours away and therefore effectively infinite. And when it lands, it will sit beside methane-carved channels and dunes of organic sand, under an orange sky, on a shore that no one has ever stood on. Stand there for a moment before we finish. The ground beneath you is damp, not with water, but with methane, held in fine dark sediment the way desert soil holds rain. Rounded cobbles of ice lie scattered around your feet, worn smooth by a current that ran through here at some point in the past and may run again. The light is dim and orange, the color of late afternoon seen through smoke, and it comes from everywhere at once, scattered by the haze until there are no sharp shadows. Above you, that haze goes up for hundreds of kilometers. You cannot see Saturn through it. You cannot see the sun as a disk. You cannot see stars. In the entire sky, there is nothing but a soft amber glow, brighter overhead, fading toward the horizon. The air is thick. It presses on you slightly more than air does at sea level here, and it is unimaginably cold, but it is calm, barely moving, gentle against the outside of a suit. And somewhere ahead, past the edge of what you could see, there is a shoreline, and beyond it a sea. It is worth remembering how recently any of this was knowable. For 350 years, Titan was a point of light. For most of that time, no one had any reason to believe it was more than a large frozen ball. The idea that it might have rivers would have seemed absurd to nearly everyone who ever looked at it through a telescope. The change came in a single human lifetime. Kuiper found methane in 1944. Voyager measured the atmosphere in 1980. Cassini arrived in 2004. Huygens landed in 2005. Everything we know about Titan as a place was learned within the past 80 years, and most of it within the past 20. That is worth holding on to because it suggests something about the state of our knowledge generally. We are not looking back on a completed picture. We are somewhere near the beginning. What Titan actually teaches, though, is subtler than any single discovery. The lesson is about the difference between conditions and processes. We spend a long time assuming that the things which happen on Earth happen because of what Earth is made of, that rivers require water, that weather requires our chemistry, that a place fundamentally unlike ours would necessarily be inert. Titan demonstrates that this is backward. Rivers are not a property of water. They are a property of gravity and slope and a liquid, any liquid, falling from a sky onto high ground and finding its way down. The process is indifferent to the substance. Change the material and change the temperature by 200 degrees and the same patterns appear. The same branching networks, the same rounded stones, the same deltas where a channel slows and drops what it carries. The universe, it seems, is not short of ways to build a river. It only needs the right temperature and something that flows. Which reframes the question we usually ask. When we look outward for places like Earth, we tend to look for places made of the same things: water, oxygen, a temperature range we would find comfortable. Titan suggests that this may be too narrow a search. There may be many ways to be a world with weather. Ours may be one variation among a great number, distinguished not by being the only possibility, but by being the one we happen to have grown up inside. And there is the other half of Titan, the part below. Beneath 100 kilometers of ice in complete darkness, at pressures nothing on Earth's surface experiences, there is very probably an ocean of water larger than all of ours combined. It has been there for billions of years. Nothing has ever seen it. Nothing has ever measured it directly. We know it exists because a small moon flexes slightly more than it should as it swings around its planet. Two liquids on one world, separated by a wall of ice, and each one, for entirely different reasons, among the most interesting places within reach. We will go back. There is a machine being built now, in clean rooms, that will fly across those dunes in the 2030s, landing and lifting off and landing again, sampling a world that manufactures organic chemistry continuously and has been storing the results in the cold since before Earth had continents. Whatever it finds will not settle the largest question. It is not designed to. It is designed to establish how far the chemistry went, which is a smaller question and an answerable one, and the kind of question that actual progress is usually made of. But even if it finds nothing remarkable, the effort will have been worth making, for the same reason all of this has been worth making. Someone ground a lens by hand in 1655 and saw a point of light beside Saturn. Someone else built a probe that fell for 2.5 hours through orange haze to photograph a plain of ice pebbles. None of it was necessary. All of it came from the same impulse, the refusal to leave a dark place unexamined. The rain is still falling out there. The channels are still filling and draining and cutting a little deeper. The dunes are still creeping eastward, grain by grain, driven by winds that blow strongly only twice in 30 years. The seas at the northern pole are slowly evaporating and will, over tens of thousands of years, reappear in the south. None of it requires an observer. It was doing this long before anyone knew, and it will continue long after. But for a brief moment, in the middle of all that time, a species on a distant blue world learned it was happening and cared enough to look. Let that be the last image. Somewhere right now, under an orange sky, methane rain is drifting slowly downward in drops the size of marbles, falling through dense, cold air, gathering into streams, and running quietly toward a sea that no one has ever seen the far side of. It has been doing that all night. It will still be doing it in the morning.